Sloth workshop. So I really appreciate you all coming here. This is very exciting. Um, this is an environment where you can expect to learn about painting, and it's also an environment where I'm expecting to become a better teacher. So we're all going to be learning here. Um, and we're not starting from zero though, so you're going to learn some good information. The information will be presented to you at a college level. So if some of the information feels kind of intense for you, don't worry about it right now. Um, the the level of information will always be there waiting for you whenever you're ready for it. So if you don't understand it completely today, or if your brain says, I am breaking down and my reality is collapsing, don't freak out and just stay calm and realize there will be future opportunities for you to learn this better and deeper. And um, but if you have questions, feel free to ask. Small and my TA Sage Sloth will be
Sloth, may I interject?
Yeah, please.
You know my friend that asked you to join. You never gave him the invite code. He's not in the server. Ray.
Shoot, could you help me with that? Do you think you could get your friend in
Yeah.
here? All right,
Yeah.
thank
What's
you.
the invite code? Because I think it's an info. Here, info. Got it.
I'm a Discord noob, so please let me know if you.
The invite code should be an announcement, actually.
Yeah, no, it's in.
Or it's in
It was in the
voice
first.
now.
It was in the first chat. It's an info.
Okay.
Didn't get an announcement. What the?
Get in here.
So yeah. So continuing on here is if you have questions, feel free to put it in the voice channel. That's 3 rooms above us with the hashtag voice, and you can ask questions in forms of text. Small and Sage Sloth will be looking at those questions. And you are also welcome to verbally ask questions. Now, there's a lot of heads in this room, so I would recommend waiting for a good opportunity to ask those questions. And I will try to stop, intermittently to see if anybody has questions. So, at one point I had to learn all this information myself. So at least anecdotally, I know what the challenging parts can be. But what was challenging for me doesn't mean it will be necessarily be challenging for you. And other parts that were easier for me to understand might be challenging for you as well. So we'll try to, lessen the mystery of some of these concepts. But like I said from the beginning, if it's very hard for you to understand what's going on, don't worry. We have time. This class is not graded. You are now working towards a degree. So there's nothing in the world that says you have to know this right now. Okay. And art students in general want to know everything right now. And it's just, as far as I know, it's not possible. And sometimes it's really nice to learn things at an appropriate time, you know. So we were talking about death earlier. Imagine if you learned about death at the age of 3, it would be pretty tragic. So, being patient about when this information makes sense to you is a good thing. And, but of course, try to balance that out with your sense of curiosity. And if you're curious about something, feel free to ask. We do want a lot of decorum in this class, and so be mindful of that. And yeah, I do have kicking powers, but I don't plan to use it. So let's just keep it that way. And let's see here. Yeah, and so myself, I've been doing art for about 5 years. I started at community college at OCC in California. I'm 38 years old right now, so I started art around 33. I have a very late start to art, beginning drawing at 33. Hadn't drawn since probably the age of 8. So big period of not doing any art. So if you're here without having done any art yourself or very little, I can very much empathize. That's in the very recent past for me. And then from there, I went to learn a little at Art Center at night in Pasadena, and also at Brainstorm School in Burbank, California. And Brainstorm School, if you don't know, is like a concept art academy in a way. non-accredited, but the teachers there are a lot of them are graduates from Art Center, and they run their courses very much like Art Center. And yeah, so you could say I'm like an Art Center student by proxy without the all-nighters. And also painting wise, I'm I'm I have spent a lot of independent time uh, exploring, learning information, and even though Brainstorm is the one that taught me how to paint, the way I paint now is probably quite a bit it's on quite the tangent from the way Brainstorm teaches painting. And yeah, but there's no wrong way to paint. There's some ways of painting that are easier to understand in general. And but what is important that all those painters share is sense of understanding how color works and how our vision works. So today we'll be covering how vision works, um, how you can figure out how objects look in certain lights. So if you have a ball that you consider to be green, what is that going to look like in blue light, yellow light, red light, green light, and white light? And so we'll be going through that, and we'll be working on form as well. And at the end of the lecture, I will be giving you demos on how to do your homework. And we'll be taking a break every hour. Sage Sloth will be taping this class, and she will be doing it in like hour-ish increments and putting it in her Dropbox. So you are more than welcome to review those videos if you missed something, or like I mentioned earlier, the concept was very difficult. And also you can give it to your friends as well. If you do give it to your friends, give me $5. And I'm joking about the $5.
Wait, what?
It's actually $10.
Yeah, don't do that.
He's
this
actually
class-
joking. It's $30 per class.
Yeah, exactly. No.
We
Start
split the
paying.
profits for each sale.
Yeah, we have to
yeah.
split it between Sage Slot, TA, the
Alright.
other TA.
No, I'm the TAA. I'm teacher's assistant.
Oh,
Well, guys,
TA.
moving on. I'm sorry for
Yeah,
making. I'm
sorry.
sorry for instigating this joke, but this class is free, and you might wonder why it's free. But it is free for the fact that I want to become a better teacher, and also it feels nice to help people. And so I hope you take this class with that in mind. And so if you have 30 questions and you're thinking, well, I need Sloth Brush's 4 hours of his week to answer these questions, you might want to dial that down a little bit. And I'm doing this on my free time, so I will not be as available as your university professors or your high school teachers. But I am as like them, I am all for you guys learning painting and being more flexible in how you approach your art. So let's get this started. Any questions before we start the lecture?
I
Yeah,
have
how
one.
long?
Okay, you can go first.
How long is this? How long will it be?
It's probably going to be, we're going to cap it at 3 hours. It might be shorter than that, but each week we're going to meet around 2 to 3 hours. Okay.
Alright.
It won't go longer than 3 hours. And if you have to leave before the class ends, feel free to. It's okay.
Alright.
For me,
Thank you.
I wanted to know, so is it only from Mondays? So like Tuesday through Friday, we won't have any classes? Is that how it's gonna work?
Yeah, Tuesday through Sunday, you won't have any classes. Yeah. So it'll just be once a week on Mondays at 3 p.m. PST. Yeah.
Thank you.
You're welcome. Any other questions? All right, let's move on. So we are going to learn today something that might be unfamiliar to you, in some ways that are familiar to you. We'll be learning the vision process. So I'm sure teachers, when you were younger, going through kindergarten and going through middle school, high school, and maybe even college, people have touched on how color works. In this class, and this is not the only way to interpret a color, but I prefer to approach it in a more like research-based way, and really understanding in the best way, in the most capable way possible for myself, of understanding how vision works. And so let's start here. So vision can be cut up into 3 general parts. So first is trichromacy. So trichromacy, you might be more familiar as blue, green, red cones. And that term is kind of going out of date because it is a bit unintuitive, but all of these cones okay. All of these cones can sense almost every other wavelength. Okay, so light is made of blue, green, red, and all the colors that you know outside of magenta. So magenta, I'm going to put over here. And most of your cones have a sensitivity to all those ranges generally. And this is the way your retina works in reaction to light. But wavelengths do have different lengths. So we have short, we have medium, and we have large. That's what the S, M, and L stand for. And this process happens in the eye. And then when your vision process goes towards the brain, this is in the thalamus now. We run into something called opponency. I don't know why I'm circling it, sorry. It's called opponency. So we have black and white opponency, blue, yellow opponency, green, red opponency. So you might not have thought of this before, but you've seen bluish green, right? Which is generally called cyan. And then you've seen let's see here, bluish red, which is generally known as magenta. Okay, and you've seen what other ones you've seen? There's one
Reddish
last
yellow.
one. Thank you. Okay, reddish yellow called orange. Thanks, Evan. Oh my gosh. If you weren't aware, I just woke up from a nap about 20 minutes ago, so I'm like a little out of it, but we'll see what we can do. So you can see these combinations, but why is it that you've never seen a bluish yellow or a greenish red? And that is very much because in the brain, we are designed to be unable to see green and red at the same time, and also yellow and blue at the same time. So these are the 4 colors that behave this way. You can see yellow and green, you can see yellow and red, you can see blue and green and blue and red, but not these 2, okay? So this should give you an indication of how important the brain process is. It's very possible through evolution we could have ended up being able to see a greenish red or a bluish yellow, but we did not. And so this is the way it is now. And as far as I know, there's no human being on Earth that can see a bluish yellow or a yellowish blue. And the last part is color constancy. Color constancy is it's an automatic process. You have no control over this. And it's the ability for the brain to see color in context. And so when it looks out in the world, you have no confusion whether a red jacket far away is still a red jacket, or a red jacket when it goes into shadow is still a red jacket. You don't literally see the color. You don't literally label the color as this color that's changing. You constantly see it as what you are familiar with in the context of the environment. So these are some of I'm going to zoom in here on these fairly classic illusions that show what color constancy is. So in this picture, we have square A and square B. These appear different. B is lighter because it's in the shadow, and A appears darker when it's in light here. But if we just color pick this A square and draw it towards the B, you will see that it is the same exact gray. Okay. And so we do have the ability to reflect on it and realize we're being tricked, but visually you'll be experiencing the difference. these in this picture, this brown and this orange are the same color. Now that's a very stark difference, right? But your brain is using the context of all the other colors and the lighting to figure out basically what this should be. But if we take this color and we draw it over here, it's the same exact brown. Okay. So these things are all working in tandem at the same time. There's no time where only one of these processes are working. And so just be aware of that as we go forward, that this is the kind of the black box that we're using. This is the process that we use to see color. Before I go on to the next one, anybody have a question about this? Holy shit, you guys are smart. Okay. And yeah.
So regarding opponency and where you said long or middle versus short and long or short versus middle, why is there
Yes.
nothing like short or middle versus long? Or is that technically included in those two?
So yeah, if our eyes had developed differently, perhaps you could have medium, short versus long. But we only have two forms of potency. So it's just a random way it ended up this way. So I would have to think if having a third opponency would even work. I have to think about that because these are going at the same time, and there's a certain math, there's a certain logic that allows us to smoothly experience this opponency. Okay. So if we added a third one, I think it would get more complicated, and certainly more complicated than I can picture right now.
Okay.
Okay.
Thank you.
Yeah. Any other questions about the cones or opponency or color constancy? Okay. So, and if you think of a question later, don't be afraid to ask on the past slides. Okay. So we have, we're gonna learn how light mixes, and we are going to learn two ways. There's additive mixing and subtractive mixing. Okay. So additive is very close to the way the cones are set up. We have red, green, and blue. And this is how your television works. So your television is basically made up of these tiny little lights, and they go on and off, they dim, they go to their maximum brightness, and you can see a wide range of gamut of colors. All these three together, when they're at their maximum brightness, you will see white on your TV. And when they're all turned off, you will see black on your TV. So I will show you the components and how they work. So if the blue light is turned off and only the green and red are turned on, you will get a yellow. If only the green and blue are turned on and the red is off, you'll get a cyan. And when you get red and blue on without the green, you will get a magenta. Okay. And this is an example of 50% intensity on each of those lights. They're the same exact lights as above, but they just dim to this more less bright configuration of the above colors. And so this, I will show you here how additive light works on a ball. So for now, we're going to learn this next. So don't be too worried about this now, the subtractive mixing. White light, as we have stated before, this is a simplified model of red, green, and blue wavelengths. And wavelengths that actually make us see red, green, and blue. That would be the more correct way to say it, and I'll explain that later. But this is coming in, hitting a ball, and a ball that we see is a cyan ball. So the red will be staying in the ball, it's being absorbed, and the things that are being reflected out are green and blue. And as we have seen up here, when green and blue light comes and it goes into our eye, we see cyan. Okay. And here's subtractive mixing. And after I do the subtractive mixing, we can ask questions about those mixing paths. Okay, so subtractive mixing is a little different in the sense that there's absorption and reflection working at the same time. So we again have the white light that is made of red, green, blue wavelengths. And then when it hits the ball will absorb some of those wavelengths depending on what material it's made of and what kind of reflective qualities it has. So in this case, we have this ball. We don't know what color it is yet, but we can figure out what color this ball is going to be by playing with these wavelengths. So let's say, for this sake, we absorb the blue and green, and so it stays in the ball and it's converted to heat. And then the only one that's left is red, and that will bounce out of the ball, and it will enter our eyeball, and we will experience this ball as a red ball. Okay. Notice how I said our brain interprets this wavelength as red, and just keep that in mind as we go forward. This will become important in some situations, so just keep that in mind. And in subtractive mixing, certain wavelengths are absorbed and subtracted from the incoming light. That's how you can remember how subtractive mixing works. So the ones that are being absorbed are essentially being subtracted from the light wave that's coming in, and what's left is, with simple math, is just the one that is not being subtracted. So to get a sense of how a ball will look in a non-white light, let's say you have red light, green light, blue light, orange light, any kind of light you can think of, you want to first establish, what does this ball look like in white light? So this red ball, if it's not in white light, will not always look this red. And we will cover that as well as we go forward, how that works. But this question, what does this object absorb and reflect in white light, is very pivotal in you being able to figure out how the reflective, or how the color of that ball, the perceived color of that ball, will change as light conditions change. So unless you plan to paint only in white light, where all your characters and your ships and googly dads, I don't even know if that's a word, I just made that up. But all those things, unless you plan to paint them only in white light, you're going to need to learn this. Okay. So here's another example of subtractive mixing. So the white light is coming in again with these 3 wavelengths. And when it hits this ball, only the red stays. So this is opposite of the above example. So the red is absorbed and the green and blue are being expelled. And I did this wrong, so please ignore this red bar. It should be this green and blue bar up here. And hey, learning, teaching, yeah. And then the result will be a cyan ball. Okay. Any questions about subtractive mixing? Okay. Any questions about additive mixing?
About the subtractive mixing.
Yeah.
Could you go back to that? What makes the first ball absorb specific light and not all of the light? Like, what's the difference between the top ball and the bottom one?
Yeah, I mean, that is really up to the material, as far as I know. So, like your skin absorbs light differently than someone else's skin, and I think we're gonna have to kind of go down to like the atomic level, I suppose, to explain that. What is helpful for you right now to know, and that's a very good question, is that not all objects absorb light the same way. Okay, so the very reason when you wake up and you see a white wall with a brown floor with a yellow table and a silver computer is just that basic idea that different objects absorb light differently. Okay, and the reason for that, I don't honestly know. You know, it could, I would imagine it's at the atomic level and how electrons and other things work. If you are interested in that, I would suggest searching for it, yeah, and trying to see what scientific papers say about that. But as for painting, it has not held me back, whether I don't know it or not. All I do is accept the fact that this object has a very specific way of reflecting light and absorbing light, and I just go with that. Okay.
I had a question.
Yeah.
So, if you kind of like, say you like put it into like an example of like, say, light was hitting like an ear or something, is that what you mean by like the light bouncing off the object? So like, say there's like the light and then the ball is like the object, right? So that would be like, say for example, an ear. So
Yeah.
the light that's bouncing off would be sort of like how you can like see through like an ear, I guess, if that makes
Oh,
sense.
Orangey, red, kind of like
thing,
that.
the
Yeah,
thing,
is it like that or?
the thing you're describing with the ear is a little different. So this ball is just there's no light going through the ball. It's just hitting the ball and bouncing off.
Oh,
Okay.
okay.
Yeah. So with your ear, you're gonna have light that bounces off, but you're also gonna have light that kind of goes through the ear,
Okay.
because it's kind of like there's like thinness in the ear, right?
Uh-huh.
So that's a little more complex. Um, so for right now, the way we're treating light here is in the more simple way, where like if you look at your car, or if you look at a tree, or if you look at a rock,
Oh, okay.
light just hits and it bounces off. Okay, without more complicated processes happening, like a gummy bear, where the light hits, but it also goes through the object at the same time. Okay, so we're just going to stick with that now. But this is a good idea for a lesson in the future. We will cover things that have specularity going through the object, and such as gummy bears, ears, flesh. Your fingers also do that too, depending on the light. And there's going to be a lot of parts of your body that can do that. So anything where the light can go through potentially has that quality of specularity. But for a ball, as far as this ball is, it's a solid ball, and no light will be going through. It will be absorbed or bounced off. Okay.
Okay. Cool.
Okay. Good questions. Anybody else?
I have a question about the thing where you wrote to get a sense of how a ball will look in non-white light. Ask what does this object absorb and reflect in white light. I'm having trouble making a connection between the two things. So if I were to give an example, if you had the same example ball that you were giving in the bottom part was the cyan ball.
Mm-hmm.
So how would that look under, let's say, a red light?
Yeah, we will be getting to that. So if you don't mind waiting just a moment.
Yeah, for sure.
Yeah, and I will show you what that looks like. And I'm just going to take this away so you're not confused. And so we will be touching on that. So if you're curious about that, that will be answered today. Anybody else for additive light or subtractive light?
I have a question.
Yeah.
So basically the subtractive light, that's just what something's base color is, right?
Yeah, you can kind of look at it that way. That's a good simple way to understand it. And in a technical sense, it will stop being helpful after a while, but it is a good way to start. So yeah, when you look at an object in front of you right now and you see that color on that object, that is the quote unquote local color, or the color of that thing, and what you refer to as the base color. Okay.
Okay.
But
I think you could. Oh, sorry.
I was just going to say, as you go along, you're going to learn there's no such thing as base color. There's just what color you're gonna see depending on the situation. Okay, but the ball will always have a consistent sense of what it absorbs and what it reflects. So in that sense, there is an objectivity to that material. Okay, so what it absorbs and what it reflects will never change. the incoming light will change. You know, it might just have blue light coming in, green, and then what reflects out as a mixture of those two will be different for each situation. But Evan, go ahead.
Oh, I was going to say, I think you could think of it as the process of subtractive mixing results in the local hue of an object.
Yeah, that's another way to say it, and it would be correct.
So is it like certain materials just absorb more of one thing? No, just reflect more of one thing more?
Yeah, it has the tendency to reflect a certain range of wavelengths.
Okay, that
And
makes sense.
some absorb certain range of wavelengths, and
Okay.
that changes from material to material. Yeah, and it gets different also. Like that's how paint works. So paint is made of different materials. So you don't just have same material paints with different colors. Every color of paint you see has different materials in it, in a very at the atomic level. So those paints you see. So when you see a yellow paint, or let's say go to match this example, you see a red paint, it's very much likely that it's absorbing a lot of green and blue wavelengths and reflecting a lot of red wavelengths. Okay. So I hope that helps. And Evan, thank you for nicely phrasing that. You do have a talent for phrasing, Evan, I have to say. So we're gonna continue and try to answer these questions. So you mentioned the cyan ball, and so that's actually going to be our first example. And so we have, in this situation, we have yellow light. These are the components of this yellow light. We have high intensity green, high intensity red, and medium high intensity yellow. So just in case you're confused about this, imagine the TV. Now the TV doesn't have yellow light, right? So it never uses yellow light to make yeah, pardon me one second. It never uses yellow light to make a yellow light. It only uses red and green lights to make yellow light. But when you're in life, you will the sunlight will have yellow wavelengths in it, and hardly ever. I think there's only like one type of yellow that doesn't have green and red wavelengths in it. It's strictly a yellow wavelength, and so you're not going to see that in nature very often, you know, if at all. So this is yellow light in nature with these wavelengths. It's heading towards a cyan ball, or a ball that appears cyan in white light. So the qualities of this ball, we can infer from this idea that the wavelengths that are likely reflected are blue, cyan, and some greens. And the ones that are being absorbed are the yellows, oranges, and reds. So we have incoming red, green, and yellows. So how will this ball appear to us? This is the painting process, okay? So knowing this answer is going to help us paint this ball in this light accurately. Okay. Now, I'm going to show you the answer to this one right away. And the next one, I'm going to let you guess. Okay. But the answer to this one is this. So in case this doesn't make sense to you, let me explain it. So incoming red, yellow, and green. When it hits this ball absorbs yellow, orange, yellow, or yellow, orange, red. So the red that's coming in from the light is going to stay in the ball. Yellow that's coming in through the light is also going to stay in the ball. Then now this ball reflects blue, cyan, and green. So the green that's entering this ball will be free to leave. And so when the green leaves, through the question mark and to our eyes, we will perceive this ball as green in this light. Okay? Any questions about that? Okay.
You said
I
it
have a-
was.
I
Okay,
feel
you
like
go.
I'm
Sorry.
still kind of like new to it, so
Yeah, absolutely.
you know.
Let it marinate. Okay.
Yeah.
Hello,
So
hello.
what's that?
Oh, how come? Why isn't the blue and cyan and the combination? If blue and
Yeah. So the reason I included this is that this is the quality of the ball that's always there, but cyan and blue is not always in a light, right? So when it's a yellow light, it's not gonna have blue and cyan. Um, it might have small negligible amounts, but it won't be important for what we're doing here. And so this is more describing the objective reality of the ball in that it always absorbs this, it absorbs this, it always reflects this. And the incoming thing is only has this. So this is kind of how you want to think about this material. And so that's why these wavelengths I included in reflected, even though it's not in the light, okay? Because that quality is always in the ball, but it doesn't mean we'll be using that quality here in context. So if it was a white light coming in, this would play a part because there's blue, cyan, green in the white light as well. But right now, this will do. And does that answer your question? Does that clarify it?
Oh yeah, I think it does. So like we can only see the light, right? We can only see the color of the light.
Yes, yeah. Anything you see in life is only because you see the light. Yeah.
Got it.
So yeah, that's a good question. Thank you. that's that's a very basic question that we should be clear on. So I appreciate you asking that.
Oh, Sloth. Angel's asking, why isn't it purple?
Yeah. So purple is unique in that that it doesn't have a wavelength. So when you see white light coming in, you will have a range from like these. Oops. From this range to this range to this range. And white light has like a mixture of these, like anything in between these two. Okay. So once you get past those two, like over here or over here, it gets a little goofy for us. So our vision is limited to the wavelengths that humans can see is limited to this. Roughly, this is like 300 nanometers in wavelength to about 700 nanometers. Okay. Now, the reason we see purple or magenta or like a reddish blue is because that to see that color, we actually need two wavelengths. Okay. And this equals this. Okay. So when you look at a white light, there is no like blue and red traveling together as a pair. Okay. So you will never have balls that are reflecting magenta or absorbing magenta. Yeah, this color magenta is, I mean, essentially every color is made up in our head, but magenta is like more so made up in our head. So don't think too much about that, otherwise your brain will turn into mush. But yeah, there is no magenta wavelength. Okay.
So do we live in a simulation then? No.
The simple answer is yes, and we're gonna move on to the next one. Okay.
I knew it.
So let's move on to this next example. So we have blue light, and the components of the blue light are as follows: little red, a lot of blue, and a good healthy amount of cyan. Now the ball we have here is a ball that appears yellow in white light. So what we can know about this ball in white light is this: it absorbs blues, and it will reflect a wide range from green to yellow to orange to red. Okay, and all in like different strengths, but this is good enough to know in a simplified way. So this is what we can infer from seeing it in white light. So now we have blue light. What's going to happen? Anybody have a guess? Well, take some time to think about it. Yeah. So
Yellowish green.
okay, so we got yellowish green.
Is it red?
Yellowish.
Okay. So try to do the math on this. Let me help you out one at a time here, or one step at a time. So these are the components in the blue light. Which of these components will stay in the ball, and which of these components will leave the ball?
The red will leave the ball.
Okay. So that's good. So red will in fact leave the ball, and the blue and the cyan will stay in the ball, right?
Yeah.
So this red is leaving the ball, but it's not a very big red, right?
Yeah.
It's a tiny red.
So it'll come out orange, right?
Well, when a red light comes out, whether it's strong or weak, it's always going to be red, or the wavelength will make your brain see red. Okay. So it doesn't matter if the energy level of that red is weak. So I guess one way to explain it is that, let's say we're seeing red at 700 nanometers. Okay. And red will always be 700 nanometers. Okay. So even if it's a small 700 nanometers, it's still 700 nanometers. And if it's a very intense red, it'll be a big 700 nanometers. So the wavelength doesn't change. So orange would make sense if for some reason 700 went to like 650, just because there was less of it. But this does not happen. Okay. So we will still be seeing red, but in a very particular way. So we have this red coming out. It's like a tiny little red. Okay. And there's no other light wavelengths coming out, right?
Mm-hmm.
Okay, so if the red is weak, do you think it'll look like this? Or do you think it'll look like this?
The latter.
Second one.
There you go.
Second one.
Yeah. So it's darker, right? It's dimmer. And you sense less red, even though there's red in there. So the answer will be this.
Huh.
Okay. Yeah. So I did push the red a little bit just so you could tell that it's red. But if there was no red wavelength here, what do you think this ball would have looked like? If there's no little wavelength in the light, what do you think this ball would have looked like then?
Black.
Yellow?
Gray.
Gray.
It'll be gray.
Or
Black.
black.
Okay. So here's the thing. So when you see things, you see the light, right? You see the light reflecting off of the object. If you don't have any red, what light is reflecting off of this object?
Nothing.
Right. And so if there's no wavelength being reflected, you would see no light. And so what would that appear as?
Black.
Black.
Yeah.
So it would appear as black, but in reality it's red.
So you're.
Well, that
It's
question,
observing.
that question I
yellow.
will answer.
Sorry.
That question I will answer to you later, when we go more in depth into that. That's a more complicated subject of asking what the ball is. Okay, but for now, try not to describe the ball as yellow or red, but try to describe the ball as what it reflects and what it absorbs.
So you're basically taking like all those wavelength colors from the top right and just seeing like what colors are right next to the thing that you're looking at currently, right?
Oh, could you rephrase that?
Okay, so like you're looking at the yellow, right? Like the yellow ball right there. And on the top right, when we look at like the different colors that are next to the yellow, it's like orange, red, and green. So that's the colors you're using for the reflected colors, right? Is that how you're connecting it?
I'm losing a little bit on what you're referring to. To be
top
perfectly
right.
honest.
Okay.
So you refer to this first, right?
No. I'm talking about the top right.
Oh, the top one. Okay,
Yeah.
this one?
Yeah.
Okay. This one.
Yeah, so you're taking that yellow right? Because the ball on the bottom left is yellow, and you're just
Okay.
taking the colors that are right next to it, right? Like the orange and red and the green.
Yes, yeah.
Okay.
So in real life, yellow light is composed more like this. So I unsimplified it a little bit for you guys here. It's a little closer to life. So when you see yellow light, its components are going to be these. And it will be in different like balances, but generally you will see this. Or these will be there. These wavelengths are all traveling together, and your brain interprets it as a yellow. Okay. So when you see this yellow ball and white light, which has all the wavelengths coming in, you will see these little guys bounce together out, and this will hit your eye, and then your brain will be like, well, of course that's yellow. Okay.
Okay.
And
May I one more question, please?
yeah.
So the intensity of the red, as you said, and the way it looked kind of darkish,
Mhm.
would that be sort of in a dark room, like the intensity of the red being reflected off an object, like being in a dark room, so it looks kind of muddy?
No, this will be in a room that has blue light. So imagine being in a. Have you ever been in? Do you guys know what a dark room is for photography?
Yes.
Okay, so in a dark room, they have a red light bulb going on at all times. But imagine that light bulb being blue. So imagine you're in a room where the light bulb is blue and it's only emitting blue light. So the room will feel darker to you in a sense because it has less light intensity. But let's say we were able to get a blue light as intense as the sun itself. It'll probably burn your eye sockets out, but let's say it's that intense. If it hit this ball that appears yellow and white light, even in midday, it will appear black. Yeah. Now it will have other things bouncing, other objects bouncing light towards it, so it might catch some of the red, so it'll still be a little bit red. But let's say somehow we were able to isolate that ball outside with just the blue light, it would be black. Okay, without the red. Now, if it had the little red, it would be somewhat red, like so. Okay, so this takes a little getting used to, thinking how can a ball be like lightless in light? Okay, but as of right now, we've researched materials. There's a YouTube video that will show you a material that very much acts like that. It's like a black material that has like 99% something absorbency and of light. So every light, almost every light wave that hits that ball don't leave that ball, no matter the wavelength. And it will look like just like a flat black disc in the 3D world. It's a very strange sight. And as strange as that is, this dark ball will also appear kind of strange to you. You just wouldn't be used to it. Thankfully, this doesn't happen a lot in regular day. But this is something. This is just an example of what's possible. Okay.
I have a question.
Yeah.
So, so like, let's say we mix purple pigment. How are we able to see that purple
if you have a purple pigment? Yeah, so a purple pigment is going to be made of materials that reflect blue and red. Okay, and that's how you get a purple pigment. Yeah.
Well, okay. So,
All right.
I just wanted to know, are all, like, let's say the blue light, are all wavelengths for a given color the same? Like the intensity of it. Like you see how the red is low intensity, the cyan is medium intensity. Are
Mhm.
all colors, given colors, have the same intensity in every situation?
Well, think of light as, I guess an easy way to think about it is, imagine you want cyan light bulbs, and you know how light bulbs come in different forms of brightness.
Yes.
So you could have a very low brightness cyan light bulb, then you can have like a medium, and like an even higher medium, and you can have like the brightest cyan light bulb. So light can work like this. So
Okay.
yeah, so keep that in mind. So this red is a little misrepresentative. Is that if that red is that dark and just traveling by itself, or this light wave, usually most likely when it hits something, and let's say the object reflects that red, it will always come out like this. But if this red was bigger, like more intense, like the blue, it will come out like this. Okay.
Okay.
So yeah. So there you go.
So can I ask a question? So from what you've said, it's kind of like a question, but I'm kind of just like trying to see if I'm understanding it right. So based on what you said, is it like our perceived range of colors based on the size of the wavelength and the frequency? Because like you'll see a red, you'll see a red more intensely than you would see like a blue light because it is a bigger wavelength. Is that what you're saying?
No. It's you will see, well, it's kind of a yes and no. The answer to that is a little complicated, but if all the lights were equally intense, you would all see them as equally bright.
Yeah.
So all the wavelengths, rather, like that's the energy of the wavelength. But the wavelength, this measurement of like 300 is not the energy. This is like the size. This is like the rate of the wavelength. And yes, red is a little larger, right?
Yeah.
Yeah, but the intensity of it is like how much energy is in it. So a weak energy will have the same wavelength, but like lot less blue. And same with red, weak energy, lot less red. Or we would perceive it as lot less red. Okay, so does that answer your question?
Yeah, I see. Kind
Okay.
of. So they're moving at the same. Never mind. I'll just look it up later because I don't know how to phrase it right now. So I'll just
Yeah.
leave it.
Yeah. Thank you for that.
Thank you.
Thank you for being patient about it. And feel free, if you still don't understand this as the days go by, and let's say you read into it and you're like, I still don't know what's going on, feel free to contact me and I'll try to answer it for you in a different way. Okay?
Okay. Thank you.
Yeah. So any other questions? Last chance?
Yeah.
Yeah.
I'm just wondering, how does the wavelength within the colored light actually affect the color light? Because just because I'm wondering, like in your blue light example, there's components of cyan and red in there as well.
Yeah.
However, we only see blue. Does that mean that it's just because it doesn't matter what's in it? It's only the most powerful one that gets
Oh
seen?
yeah. So I can see why you would see that, but no, think of this, and it is a bit misleading, but think of all these together will make your brain see that. Okay.
okay.
So yeah. So these are all in there working together as far as humans are concerned. So we don't see these separately, but if you measured this light to see what's in there, you would see these. Okay.
Okay.
So yeah, it's kind of
So
like
I think I'm misleaded because you have that blue component which looks exactly like your blue light.
yeah.
So technically it wouldn't actually be that like particular blue. It wouldn't be the same blue as the blue reflect coming out.
Right. Yeah, the
Okay.
end result blue light will look a little different than this.
I see. It's a mixture of all the components.
Yeah.
Okay. Thank you.
Yeah. So I do try to say it's simplified. So try not to take it too literally. But in future slides, I will adjust this blue because you make a very good point. So I'll adjust this blue a little bit so it doesn't look identical to this one. Okay.
Thanks.
All right. No, thank you very much for that observation. Appreciate it.
Of course.
Question.
Yeah.
So if we were to properly like render out the yellow ball getting hit by the blue, right? Then the areas that will hit the light that is being lighted, the halftone up till the halftone, that part will be like gray, and then as it gets darker, darker area, then it will be turning into desaturated yellowish.
It, in this sense, yeah, it will. It will. So I think you're still a little attached to the fact that the ball is yellow. If you go in that route, the answer. So try to forget that the ball is yellow, and just remember what it reflects and what it absorbs. Okay. So since there's no yellow wavelength in the blue light, you're not going to see yellow due to wavelengths in the shadow. And now there's a complicated thing where you actually will see some yellow in the shadow, but that's due to not the wavelengths, but more how your eyes work. Okay, so or how vision works. So I will touch on that later too, when we talk about creating light and shadow. Okay.
Okay.
Yeah. But good question, and a lot of good questions here, guys. So thank you very much. They're thoughtful questions. So I think this is a good time for a break, and we will start talking about this next. Okay? So I will leave this up here if you want to just sit here and study it a little bit. But thank you very much for hanging in there for the first hour. And if you have any questions when I come back, feel free to ask them before we move on to the simultaneous contrast. Okay?
How long is the break for?
So let's all meet back here at 4:05.
4:05. Okay.
Okay.
PST?
Yeah, 4:05 PST.
Well, I hope it's not a fucking like 2 hour long break.
2 hours, no.
2 hours later.
Yeah, so see you guys in about 8 minutes, okay?
Oh, Sloth,
Okay.
hold on.
Yo, Wamba.
Sloth,
Yeah.
could you zoom in a little so I can't read the text?
Oh yeah, sure. This is about as much as I can zoom in. Can you read it now?
Yes, thank you.
Okay. Yeah.